These slides will begin our discussion on topics in Chapter H, which begin coverage of the hardware features of the PIC24 microcontroller. Let's spend some time talking about C and embedded systems. A microcontroller-based system using a device such as a car engine performing control and monitoring functions is referred to as an embedded system. The embedded system is invisible to the user. The user only indirectly interacts with the embedded system by using the device that contains the microcontroller. It turns out that many programs for embedded systems are written in C. The reasons for this are many. Here are a few. First of all, C is portable. That means that the code can be retargeted to different processors. C has improved clarity over assembly language. That means it's easier to read and understand C programs than assembly language programs. This is important from a maintainability viewpoint. Finally, modern compilers produce code that is close to manually tweaked assembly language in both code size and performance, and so there's less need to actually write programs in assembly language. So the previous slide mentioned that many embedded systems are written in C. So what if we spend several chapters learning how to write PIC24 assembly language? Well, it's easy. You now know that the way that the C is written can impact assembly language size and performance. You now know that if you use a 32-bit data type instead of an 8-bit data type, that you're going to get larger code and slower code as a result. So you would only want to use an 8-bit data type if that was all that was needed by your application. You also know that learning the assembly language and underlying architecture of a target microcontroller can definitely provide you some clues in terms of how well the compiled C code is going to execute. As an example, if the microcontroller has hardware support for multiply and divide in terms of instructions, then you know that those operations are going to be executed efficiently by the microcontroller. Given all that, however, sometimes you do have to write assembly language code for either performance reasons or for size reasons. So at this point, you know how to do both. But whenever we cover future hardware applications in the rest of this course, we are going to do it in the C language. The steps of a typical C compiler are shown in this slide. Given a C file, the first translation is to translate the C code into unoptimized assembly code. At that point, several optimization steps can be done on the assembly code in order to reduce both its size and improve performance. This assembly language code is then going to be assembled into machine code, which will be a .o file, an object file. This will be done for each C file in your project or application. At that point, all the object files are combined together into one file, an executable, which in our case is going to be a hex, what's called a hex file, that would then be able to be downloaded into the PIC24 microcontroller. Here's just a simple example of an optimization that a typical compiler might do. Here we're doing I is equal to I plus j. Here we're doing k is equal to k plus j. If you simply assembled compiled each line separately, you would get something like this. However, an optimization step here can note that j is actually shared between these two statements and is in W0, and one statement can be eliminated from this 4-statement implementation to form a 3-statement implementation here. But there's many other optimizations that can be done by a compiler. For the hardware projects in this course, we're going to use the MPLAB PIC24C compiler. It's a pretty good compiler. It's based on GNU-C, which is a freeware compiler, and that's been around for years, and it generates good code. And we have a zip archive that has all of our example projects. They're organized for chapters, so you'll see code organized by chapter 8, chapter 9, and so forth. Each one of these things is going to have many project files in them that will list all of the book examples. You should use these project files whenever, as a start, whenever you're actually doing your laboratory assignments. When you're examining the C code that comes with the examples in the book, you see that all of them have a statement at the top that says include pic24.h. This will include lots of different header files that are needed for our library functions, and also include microchip include files as well. One of the things that we're going to be doing in the C code is to be accessing special function registers. It turns out that the PIC24 has many special function registers other than the ones that we have previously discussed, and they're all declared in these various header files that are provided by Microchip. Here's an example of a typical special function register that is declared, one that's called port B. Typically special function registers are going to be in all uppercase, and you can refer to these things just like variables in C code. So here I'm assigning the special function register port B the hex value F1000 in my C code. Often we'll find it necessary to refer to individual bits within special function registers. This slide shows one way to do it. Here we're going to use a special function register named port B, append to it bits dot RB5. This is going to refer to bit RB5 in port B, and here we're setting it equal to a 1. Here we're going to set RB2 of port B to a 0. We can also test bits in this way. Here we're going to test RB0 of port B to see if it's a 1. If it's a 1, then we're going to execute this if body. We'll also find that there are bit fields defined in special function registers. A bit field is a grouping of consecutive bits. These bit fields are named, and we can assign these bit fields a value. Here we are assigning the bit field INOSC and the OSCON special function register a value of 2. We will discuss all of these special function registers whenever we get to the hardware module, in our coverage of PIC24 hardware features. If a bit name of a special function register is unique, then we can just use the underscore the bit name to refer to it. This makes it a little bit easier. That way we don't have to remember the register name. Here we can simply refer to bit RB5 of port B as simply underscore RB5 and set equal to a 1. We can also refer to bit 2 of port B as simply underscore RB2 and set it to a 0, and so forth. This is going to be a preferred method of referring to bits within special function registers and bit fields within special function registers. The default runtime code generated by the C compiler is going to initialize global variables to 0 if they do not have an explicit initialization value. So for example, this global variable here, U16K, does not have an explicit initial value, so it's going to be initialized to 0, while this one here will be initialized to 4 before entry to main. Occasionally you would like to have a variable that is not touched by the C runtime code. If you use this macro here, underscore persistent, in front of a global variable, it will not be initialized by C runtime code. We'll see a reason why you might want to do that in a later example. You will discover that our support library and code examples make extensive use of C macros and inline functions that are declared in header files. The naming convention is all uppercase. Here's an example: pound define default baud rate 57600. There are two reasons for using these. One is to improve code readability. This name is more readable and understandable when you use it in the code instead of actually using just a number. The other reason is that if this is used several places in source code, instead of having to go to each place in the source code and change it to a particular number, we can simply change this value in one particular header file, and then that will propagate to all uses in the source code. We also make use of static inline functions a lot. What an inline function does, it expands to its body statements without the overhead or the subroutine call and return. This means that this thing is a static inline function is a bit more efficient from an execution speed viewpoint than a true C function. This is the particular device variant from the PIC24H family that we'll be using in our examples. This device comes in a 28-pin DIP package. DIP stands for dual inline pins. It means there's a row of pins on each side of the package, and it's easily able to be plugged into a breadboard. This picture here shows the device pinout from the PIC24 datasheet for this device. You will note that most pins have multiple functions. This looks a little bit intimidating at this point, but don't worry, we'll cover these multiple functions as we come to them in our discussion of the various hardware features of this particular device. These pin functions are all controlled via special function registers on the PIC24. This diagram shows the initial schematic that you will wire up in your first PIC24 hardware lab. I know it looks intimidating. Don't worry, the lab has a step-by-step wiring procedure for producing this schematic. At this point, let's talk about powering our PIC24. This particular PIC24 variant requires a stable 3.3 volts DC. The power pins on the PIC24 are labeled as VDD, while the ground pins are labeled as VSS. There are two pairs of these, and they need to be connected together. We're going to power this device by using a wall transformer which converts the 120 volt AC to 6 volts DC. This is then going to go through an on-off switch that you need to hook up. You'll want to turn power off and on via the switch and not by simply unplugging or plugging your wall transformer. Following the switch will be a fuse. The job of the fuse is to protect the rest of your circuits against high current flow in case you accidentally connect power and ground together, causing a short. This fuse will blow when high current flows. Typically, we provide a fuse that will blow at about 200 milliamps trigger point. This device is called a voltage regulator. Its job is to take the DC voltage produced by the wall transformer and produce a stable 3.3 volt output regardless of how much current is drawn by the circuit within limits. You will note that there are some capacitors on either side of this voltage regulator. These are needed for correct operation of this regulator. You will also notice some 0.1 microfarad capacitors connected between VDD and ground here, and also between VDD and ground here. These capacitors are called decoupling capacitors. It turns out that when the transistors in this microprocessor switch, and they can switch rapidly, then the current requirement into this pin can change very fast in a small amount of time. It's the job of this capacitor, which is basically a charge bucket, to help supply that change in current. When you hook these up on your breadboard, you should place these as close to these pins as you can. This capacitor here, connected to the V cap pin, has the same job as this capacitor here connected to the output of the voltage regulator. Even though the input voltage to this pin here is 3.3 volts, it turns out that the PIC24 has an internal voltage regulator, and internally this guy operates at 2.5 volts, and this capacitor here is essentially the capacitor on the output of this internal voltage regulator. You note that the value is 10 microfarads. Again, it should be placed as close to this pin as possible on your breadboard. This LED here, light emitting diode, serves two functions. One function is as a power LED, connected in this fashion to VDD through a resistor which limits current to the LED. What's going to happen is that when we turn on power and we supply 3.3 volts, this LED will come on. This will give us a nice, warm, fuzzy feeling that when we turn the switch that we actually have 3.3 volts here without actually having to put a multimeter and measure it. It's also going to serve as what we're going to call a heartbeat LED. We're going to be able to blink this LED by using this output pin RB15 during normal program operation. We're going to configure this pin in a special mode called open drain. We'll talk about that later on when we talk about the PIC parallel output ports. We want to note that this is not the normal way that you hook up an LED. It's only done in this way because we want this LED to have two purposes: one to be on when power is applied, and one to be able to be blinked whenever we bring RB15 low. We'll talk more about this configuration later. This connection here is going to be used to connect up a serial port connection between your portable PC and the PIC24. We're going to use this for two purposes. One purpose is to be able to download programs into your PIC24 without any other special hardware except for a USB to TTL serial cable that we're actually going to provide you in your part kit. The other thing that we're going to use it for is that during normal operation of your program, we're going to be able to print messages out to the PC and display that in your PC. We'll also be able to type things in on your PC and send it to the PIC24. So that way we'll provide some user interaction with your code during program execution. This connection we don't have you wire up during the lab. It's an optional connection. What this is used if you have either a PIC-Kit 2 or PIC-Kit 3 programmer, you can download a program into the PIC24 using those two special devices via this connection. This input here is called the master clear input, and when it is brought low, it resets to PIC24, forcing a jump to location 0. We hook up a switch here and a pull-up resistor to VDD. This is a push button switch. When we push it, it's going to short this, bringing this low, and we'll reset the PIC. This would be a way that you can, if your PIC24 gets in an infinite loop, you can push this button and reset it. You could also cycle power and accomplish the same thing by toggling this power switch. This slide shows the clocking subsystem for the PIC24 microcontroller. There are 3 options for generating the primary clock, which is the clock that is used by the CPU to fetch and execute instructions. The most convenient option is an internal fast RC oscillator. RC stands for resistor capacitor network. It generates a clock that has a frequency of 7.37 megahertz. It's convenient in that it does not need any external components. However, it's not that accurate. It can vary by plus or minus 2%, and it's affected by the external temperature of the device. Because of its convenience, this is the clock that we're going to end up using in our lab experiments. Some applications need a very accurate clock, or one that is very stable with regards to external temperature changes. In that case, you would simply take an external crystal with a couple of external capacitors and hook that across these 2 pins. If you do that, this circuit right here will cause this crystal to begin oscillating once VDD has been applied, and it will generate a clock signal. The only drawback with using an external crystal is that it can take a millisecond or 2 for this thing to begin oscillating, while the internal fast RC oscillator would begin oscillating essentially immediately once VDD is stabilized. Yet a third option for generating a clock is to simply apply an external clock signal to this external pin, where this clock signal is generated by some external source. In addition to the primary clock, there's also a secondary clock that can be generated by using an external oscillator across these 2 pins here. Typically, this is used for 32768 kilohertz crystal for real-time timekeeping applications, or you can actually simply have it as another clock source that you can dynamically switch between during your applications. Yet a third clock that's actually in the PIC24 is this internal low-power RC oscillator. This guy is used by some of the other subsystems on the PIC24, particularly the watchdog timer, which we'll talk about later. Once the primary clock source has been selected as either the internal fast RC oscillator, the external primary oscillator, or an external clock, you have the option of taking that input clock source and then boosting it to a higher frequency by using a subsystem called the phase lock loop subsystem. What this subsystem will take that input frequency and can boost it to a higher frequency. In this case, the maximum frequency it can be boosted to is 80 megahertz. This is going to be the clock frequency and the method that we're going to use in our lab experiments. So we will always use in our calculations, typically we will use a clock frequency of 80 megahertz, which makes for an instruction cycle frequency of 40 megahertz. This phase lock loop subsystem is controlled by some internal registers whose settings are plugged in this equation to determine how much the external frequency is boosted to this new primary clock frequency. We are not going to hold you responsible for the details of this subsystem. You can read about it in the PIC24 datasheet. To close out this initial introduction to PIC24 hardware features, we'll mention that there are special bits called configuration bits that are stored in program memory at special locations that control various processor options on power up. For example, when the processor powers up, how does it know whether or not to use the internal fast RC oscillator, or an external crystal, or an external clock? Well, that option is going to be set by configuration bits, and because they're programmed in non-volatile program memory, then they're available at power up. There's a file that's going to be included in all of our sample programs called pic24config.c that specifies the configuration bits used for our lab exercises. We're not going to cover the configuration bit details in this class. You can refer to the PIC24 datasheet for more information if interested.